Well, hello everybody and welcome to Coffee with Caleffi. This is Kevin Freet at our North American headquarters in Milwaukee, Wisconsin, sitting in for Bob Hot Rod Rohr, who is somewhere up in Montana today doing some customer training. I'm very excited to be hosting today's webinar, Pipe Joining and Plumbing and Hydronic Systems. So today, John Siegenthaler is joining us. I want to go ahead and welcome John and pass the baton over to him.
Well, thanks, Kevin. Good to be with you. I know we've got a good sized audience today. We've got a mix of engineers, contractors, wholesalers, excuse me. And one of the things that, we try to do at Caleffi, we try to solicit good feedback on topics for Coffee with Caleffi as well as Hydronics. Today's reference is going to be the latest issue of Hydronics, number 26. This was officially released a couple weeks ago at the AHR show. It's available as a free downloadable PDF file on the Caleffi website. And if you have a subscription, a free subscription, you'll be receiving that in the mail. But we're going to go right into a poll question. And I'm going to turn it back over to Kevin to read through some possible topics for future Hydronics and solicit your feedback.
Yeah, thanks everybody. So this is a wish list for future Hydronics. So please choose your top 2 favorite topics. If you could all select your top 2, that would be great. And that would really help us determine what to do next. So go ahead and pick those 2. We'll take just a few seconds here, and then we'll look at the results of the poll.
Yeah, and just a reminder, while that poll's coming in, Hydronics number 27 will be coming out in July, and the topic is going to be air-to-water heat pump systems. And this is based on a very good response that we had from a Coffee with Caleffi back in October. So we do listen and appreciate your feedback.
Yeah, so here the results are in. The top choice is heat exchangers and hydronic systems with 60%. That's a great topic. The next one, John, is hydronic solutions for low energy and net zero buildings. So 50% selected that one. Followed by valves in hydronic systems, application of PRVs in plumbing systems, and then finally panel radiator applications. Well, thank you very much, everyone, for that feedback. It's great information. Go ahead and turn it back over to John.
Okay, and again, yes, thanks for that input. So we're going to move ahead into today's topic. And what we're going to do is we're going to look at different piping materials and different joining methods that are commonly used in plumbing and hydronic systems. And of course, keep in mind, there are hundreds of different types of piping materials, some very exotic joinery methods that are being used. So we can't cover everything, but we are going to focus on traditional as well as contemporary materials. Primarily, we're going to divide that up into metal pipe materials and the joining systems that are used with those, and also into polymer piping materials and the corresponding joining systems. So think of this as kind of an introduction to the basic fundamental materials and methods used to put these piping systems together. And as we often do with hydronics and with Coffee with Caleffi, we try to start with a historical perspective. And if you do some research on piping, you'll find that it goes back thousands of years. Actually, it's probably one of the most fundamental creations that has allowed civilization to advance. So as is often the case, we can trace the piping materials back to the Egyptians with some clay material, as well as some pounded lead sheets, bamboo, as well as logs that were hollowed out and used. And the hollowed log piping was actually used in the US even back in the 1800s, specifically out in the Pacific Northwest. They actually found that some of the redwood material would hold up very well over a long period of time and use that as piping. The Greeks were involved with it, with stone and clay piping. And you can even see in the photographs there over on the right some very early valves that were fashioned I'm not sure exactly what material it was. Probably it had lead in it if it wasn't all lead. And that's traceable back to the Romans. And of course, we've evolved over centuries into much more modern piping materials, metal materials, steel, stainless steel, and several different types of polymer materials that we're going to get into. Again, bringing the timeline forward back in the 1600s, some of the hollowed logs were being used. Cast iron pipe, you see a sample of some of the early cast iron pipe over here on the right, being used back in France for one of the castles. And then as chemistry and metallurgy advanced during the 1800s, iron pipe gave way to steel pipe and different types of production methods, cold rolled steel, hot rolled steel, and so forth. And through the 20th century, especially period following World War II, a lot of developments in polymer piping materials. Some of the first PVC and CPVC, and then probably going back, I'd say early 1980s is when PEX tubing, which we look at today as more or less a commodity piping material. PEX came into the North American market in the early 1980s. And there are several spin-offs, PEX aluminum PEX, another material we'll talk about today, polyethylene of raised temperature PERT tubing, and polypropylene tubing as well. So when we're working with piping systems, we're working at a lot of different levels. Engineers, architects, contractors, wholesalers, they all need a system of communication so that obviously when we describe a fitting in particular, we want to be able to use a common terminology. So the standards that have developed today, and this would mostly apply, some of this applies to all pipe fittings, some of it is specific to copper. So some of these abbreviations that are used, the letter C, when you see that used as part of a description for a fitting, that implies that the connection is designed to be soldered or brazed with copper tubing. So C, obviously coming from the word copper. Now, with other fittings, both metal fittings and polymer pipe fittings, F or FPT stands for female pipe thread. Kind of the contemporary term for that is internal pipe thread. Obviously, the opposite of that would be M or MPT. And again, you would see this in a designation for a fitting that implies male pipe threads. Contemporary version of that is external pipe threads. And then the abbreviation FTG, fitting, that refers to a connection where the connection on the fitting itself is designed to slide into a socket on another component. It could be another fitting, it could be a valve, but there are circumstances where the fitting type of connection is used as opposed to a C-type connection. And we'll get into some illustrations that show that. Start off with a very basic fitting here, a coupling. Pipe in and of itself isn't much good without methods to join it together. So one of the most common joints is a simple coupling. So up at the top, you see an example of a standard coupling, and many fittings, especially wrought copper fittings, have a stop. And the purpose of the stop is simply to prevent the tube from sliding all the way through the fitting. So that upper fitting has a groove that has been mechanically created in that copper to stop the tube on both ends. But sometimes you may have to make a coupling where you want to slide the fitting all the way over one tube, align the other tube, and then slide that coupling back, center it on the joint, and then solder it in place. And that uses a fitting called a slip coupling. And the implication of the word slip meaning you can slide it all the way along a tube, align the other tube, bring it back, solder it in place. And then finally down at the bottom, reducer couplings when you're changing pipe sizes. Typically reducer couplings are available to change up to 2 standard pipe sizes. So for example, from a 2-inch pipe down to an 1.5-inch pipe, or from a 2-inch pipe down to an 1.25-inch pipe. Those would be readily available. Beyond that, there are some special reducing couplings, but they're not typically something you're going to find in stock at a wholesaler. You may have to special order them if you're trying to go from for example, a 2-inch pipe down to a 3/4-inch pipe. That fitting probably exists, but it's a non-standard fitting, and as such, it's going to be fairly expensive, and it's probably going to be a special order. You can find lists of hundreds, probably thousands of fittings in catalogs from companies like NIBCO. And just a bit of trivia here, if you've ever wondered what NIBCO stands for, it's actually North Indiana Brass Foundry Company. I guess they dropped the F. Today they're pretty much branded as NIBCO, but they're one of the larger suppliers in North America for a wide variety of these fittings. So we've shown some of their fittings in the slides here. Another very common fitting is an elbow, where we're going to make a turn in the piping. Typical elbows for copper tubing would be 90-degree turns and 45-degree turns. When we get up into some of the drainage, waste, and ventilation piping, you can find elbows that are actually 22.5 degrees. So putting two of those together would give you a total of a 45-degree change in direction. And in some cases, it's necessary to use a combination of these different angles to get pipe from a certain point to another point without actually bending the pipe itself. Now, in the middle of this screen, you'll see some cross-sectional drawings here, a standard 90-degree elbow, and you'll see this designation C by C. Well, that means a soldered copper socket connection on both ends of the fitting. Over to the right of it, here's a C by FTG, or C by fittings, and you'll see the lower connection here is identical to the other elbow with a socket that's designed to have a copper tube slide into it and be soldered, but the other end slides into the socket of another fitting or perhaps into a valve. Oftentimes this is called a street L, and I'm not exactly sure where the term street came from. It's one of the words that I guess you'd call it plumbing jargon, but most plumbers and those that work with hydronics, when we talk about a street elbow valve, they'll understand what you mean. And again, back to the communication. Perhaps somebody new to the industry might not know what a street elbow is, so designating it as C by FTG, that's non-ambiguous. Down below here, same ideas, only with a 45-degree change in direction. And then over here on the right, we're looking at the difference between a standard short radius fitting versus a long radius elbow. It's probably safe to say it's more common to see the short radius fittings being used. The long radius fittings are more expensive. One of the advantages of a long radius L is there's less of a pressure drop through it. There's less turbulence created as the fluid turns. So in certain applications, you can use that. So that's kind of an overview again of elbows. So let's move to another common fitting, of which there are many variations. Up here at the top, we'll start with a standard T. We're going to make a branch connection in a pipe. So we're looking at a cross section up here at the top of a C by C by C fitting. And we could put a size in front of that, for example, 3/4 inch or 1 inch. And that's referring to the nominal pipe size that would join into that fitting. So the standard T is going to have the same size connection on all three ports. But now we can get into very specialized Ts. And down here at the lower right, you see an example of a pretty specialized T here. One socket connects to 1.25 inch copper. The other end connects to 1 inch copper, and then the side port connects to 1.25 inch again. So we need a way that's non-ambiguous to describe the three sizes that are present on that fitting, especially if it's something as specialized as what's shown here in the bottom center. We've got a 1 inch copper tube coming in from the left. We've got a 1/2 inch copper tube leaving on the right. And then up above on the side port, we have a 3/4 inch tube. So do we call this a 3/4 by 1/2 by 1, or do we call it a 1/2 by 3/4 by 1, or what order should we describe it as? Imagine yourself on a phone call, you're talking to a supply house, and you're trying to order this specific fitting. How do you describe it? The protocol is you always start with the larger of the straight through connections, what's called the run of the T. Excuse me. So the run of the T would be the straight line through the T like this. So we start with the larger connection. So we start with 1 inch, and then the protocol is go to the other straight through connection. So the next number we would specify would be 1/2 inch. So far we're 1 inch by 1/2 inch. And then finally, the last number that would be specified for size would be the side port. So this is a 1 inch C by 1/2 inch C by 3/4 inch C reducer coupling. And again, that's a very specialized fitting. You're probably not going to find that on the shelf at Lowe's or Home Depot. I can pretty much guarantee that. You probably won't find it at even other wholesalers that might specialize with hydronics or plumbing fittings, but it does exist. It is manufactured. It's just going to be a special order product. Over on the far left there, you see another example of a kind of a specialized T. This is a 1 inch by 1 inch by 3/4, but you'll see the side port, the 3/4 inch port, has a pipe thread in it. So again, our designations apply. A 1 inch C by 1 inch C would mean the two straight through ports here are going to be 1 inch nominal pipe size copper soldered connections, and then that 3/4 inch side port, that could be a drain valve. It might be in a connection to some other type of device, possibly a temperature sensor. Something could be threaded into that. But I put it in just as an example to show you some specialized fittings, and again to demonstrate the consistency of starting with the larger of the straight through ports on the T, going to the other straight through port as the second number, and then finally the size of the side port. Let's move on to unions. Unions were designed to allow a pipe to be disassembled if necessary, disconnected from a component, especially if that component might have to be removed for service. For example, a circulator is one possibility. A boiler would be another possibility. Perhaps some type of a filtering device. Anything that has to come out of the piping or potentially has to be removed from the piping system without getting out a hacksaw or getting out a torch and undoing the joint that way. And you can see at the bottom, there's a wide variety of unions. There's metal unions, there's polymer unions. In the metal unions, you have threaded connections. So again, in this case over on the far left, this is a whatever the pipe size is, let's say 1 inch, F by F. So both connections are female pipe threads on that. The next one over, C by C, soldered pipe connections. The PVC union here, I don't have a pipe size down, but that would be a solvent well connection. You might see something like that used on a pool filter system. And over here on the far right, we've got a specialized union. This is called a dielectric union. And what a dielectric union does is allows you to transition from a copper pipe to a steel or an iron pipe without actually having an electrical circuit between those two pipes. And you'll see right here this orange sleeve, and the part that you don't see is there's also an O-ring or a gasket inside. And when you put the mechanical parts of this union together, the copper, or excuse me, the brass portion of that union and the steel portion of that union are electrically insulated from each other. And that's important because if that is, if you use a standard union, if you join copper and steel pipe directly and the fluid has electrical conductivity, there's going to be a galvanic corrosion over time. And you'll see this, and in fact, I would suspect many of you have seen this. Typically, you'll see corrosion, surface corrosion on the steel or the iron pipe. It's the less noble material, so that's where the oxidation is going to occur. Now, the other thing that's important to understand, a fundamental about a union like this, is that the threads on the union, up above here, you can see the union assembled, and then over on the right, disassembled. The threads do not create the seal. The seal in a metal union like this is a precisely machined metal-to-metal seal. And the threads simply draw the two parts together and create the seal at those machined metal surfaces. Some of the polymer unions like this, some of them have those machined or beveled surfaces that lock together for the seal. Others do have O-rings that are compressed against two flat faces, and that provides the seal. Okay, we'll move on to adapter fittings. Very common fitting whenever a copper tube, or in some cases a PVC or CPVC tube, basically a smooth tube, has to be joined to a threaded connection. It could be a valve, it could be a pump flange. We're going to use an adapter fitting. So we have male adapters that would transition from a copper tube to a male pipe thread, and then over in the upper right, a female adapter. And these use standard tapered national pipe threads. Again, you can see examples of a male adapter here in copper. Here's a female adapter in copper. Here would be a male adapter in PVC. And then finally, over here in the lower right, here's a female adapter in PVC, and you'll see the note on there. It says, "Be careful with this." And what happens, or what could happen with this type of a fitting? Imagine you're threading a metal, it could be a brass pipe nipple or some other type of metal male threaded connection into this fitting. As you draw the threads tighter and tighter, you're putting a lot of radial stress on the plastic, and eventually you'll split the plastic. And it's actually pretty easy to do that. And I've done that several times. So be very cautious if you're doing something like that. Normally, we try to avoid that type of a setting. Another problem you can get into with metal pipe with a male thread threaded into a plastic pipe with a female thread is, as the fluid that's going through that connection warms that joint up, the PVC will expand at a faster rate than the metal. So just imagine the outer diameter of the plastic fitting expanding away from the metal. And of course, what that does is it causes the threaded joint to loosen up. And we have seen these types of joints in the past where they will leak when there's a hot fluid going through there. But once that fluid cools down and the plastic shrinks back, they don't leak anymore. And obviously that is not a situation that you can tolerate. So in general, we try to suggest that if you're using this type of a fitting, I would only use this with a PVC or a CPVC male thread that would be going into that FPT adapter. Now, we've talked about a lot of the basic fittings. Let's talk about piping a little bit. And of course, the default piping material certainly in residential like commercial hydronic systems is still copper water tube. And copper water tube is manufactured and has been for decades in 3 standard wall thicknesses, and they're designated as type M, type L, and type K. The most common wall thickness in hydronic applications is type M. That's the thinnest wall. And if you look at the chart over here on the right, you'll see that even type M tubing can take quite a bit of pressure. That last column over here shows the pressure rating based on a limitation in water temperature. And you'll notice the pressure ratings do decrease as the size of the tube goes up, but those pressures are several times greater than a typical relief valve setting on a hydronic system. So type M copper tubing from a pressure standpoint is easily able to handle the stresses that would build up. Type L is commonly used in water distribution piping. I can remember at one point where type L, at least in New York State, was mandated for any type of domestic water distribution. The code didn't actually allow type M copper to be used. I assume the thinking was that a thicker wall, from a standpoint of pressure, probably not as much of an issue. Probably looking at it from the standpoint of corrosion over time, a thicker wall in theory would last longer. But that code has been changed. Type M is allowed in domestic water piping, at least in New York State. I'm not sure if other major codes recognize that or not. Type K is the thickest pipe. Traditionally, that would be used in underground applications. But copper piping in underground applications, for example, a water service coming in from a street main, it's not used much at all for that type of application anymore. There's just other polymer piping materials that are much more common and certainly lower cost. So you didn't see a lot of application for type K. Now, all three of these wall thicknesses have the same outside diameter. So a type M, a type L, or a type K tube would all slide into, for example, a copper elbow. They all have the same outside diameter. Another type of tube that is used is called ACR tubing. That would be air conditioning and refrigeration. It is a different size standard. ACR tubing, when we talk about, for example, a 3/4 inch ACR tube, that 3/4 inch refers to the exact outside diameter. So it would be 0.750 inches exactly. With copper water tube, which is what we use for plumbing and hydronic applications, when we talk about a 3/4 inch tube, we're talking about a nominal, and the word nominal just means approximate. So a 3/4 inch copper tube is actually not exactly 3/4 of an inch on the inside or the outside. The inside diameter you can see in this table here is 0.811 inches. The outside diameter of copper water tube is always 1/8 of an inch beyond the nominal size. Excuse me. So, for example, a 3/4 inch copper water tube would have an exact outside diameter of 0.875 inches. So again, these are common standards. These materials have been around for decades. We'll switch over to steel. Steel's got kind of an interesting history, but steel pipe is commonly used in commercial or higher pressure hydronic applications. It's also used in steam applications. When we talk about pipe sizes, we're talking about nominal inside diameters up to 12 inch, and then it switches. The pipe size refers to the outside diameter of the pipe. Years ago, probably I should say decades ago, when steel pipe was first being manufactured, the sizes that were created were referred to as standard heavy wall and double heavy wall. And those are kind of subjective. Today, those text or word descriptions have been replaced by what's called Schedule 40, Schedule 80, and Schedule 160. And there's a website here that if you need to know the exact inside or the outside diameter of these pipes, honestly, I don't remember most of these. There's just too many of them to remember. But you can go online and very quickly look up the exact inside and outside diameter for these different pipes. As far as hydronic systems, using steel pipe, it's typically going to be Schedule 40. Again, most hydronic systems, the pressure relief valve sets the maximum pressure in the system, and a Schedule 40 steel pipe is very much able to handle those pressures and many times over. Stainless steel piping. Again, you can go to that website to get the exact inside and outside diameters. Stainless can be welded, it can be threaded. You'll see in that photo there's actually some welded joints over here. There's some flanged joints. Stainless piping would be used in food processing. It's used to handle, for example, milk and other liquids in food processing. In some cases, it's used to handle medical gases. Typically anything that has to have a sanitary condition to it, or a fluid that might be corrosive to a standard carbon pipe could be handled through a stainless steel pipe. It is quite a bit more expensive than standard carbon pipe, so it's not as commonly used in closed loop hydronic systems. But in open loop applications, something like a cooling tower, where there is oxygen available to the water, stainless steel pipe is going to have much more resistance to corrosion than standard carbon pipe. Cast iron, what's modern use of cast iron is what's called a no-hub cast iron pipe. I should go back in time a bit. Before these types of fittings were available, cast iron pipe was put together with what's called a bell and spigot system. The end of a fitting or the end of a pipe would be flared out and create what's referred to as the bell. And you can almost think of that as a socket, sort of like on a copper fitting, a flared out area. And then the other end of the pipe would slide into that. And to actually seal the joint, there was a product called oakum. And some of you may remember this product. Oakum was a hemp, almost like a rope material that was soaked in some type of a petroleum product. I'm not sure exactly what it was, but I can remember handling this stuff, and it's kind of nasty to handle it. But you would pack the oakum into the space between the pipe and the socket, and the final seal was done with poured lead, where a plumber would use a blowtorch to heat up lead, and they would actually pour that in a molten state right on top of the oakum, and it would cool and solidify and provide a nice tight joint. That's a skill I honestly have never had a chance to develop and probably won't, but it's a skill that I certainly respect the old-time plumbers using that. Today, most cast iron pipes put together with these clamp-type fittings, what are called no-hub fittings. It's a pretty simple idea. You slide the pipe into the fitting and get out your nut driver or your impact wrench, and you pull the clamps tight, and that creates a seal between the fitting and the pipe. That's mostly used for drainage, waste, and ventilation today. Now, again, we've talked about different metal pipe materials. How about joining methods? Soft soldering, probably still one of the most common methods. I hesitate to say the most common method anymore because press fittings are really catching up quite a bit in hydronics. But over here, you can see some examples of very well soldered, nicely done soldered, what's called soft soldering, using either a tin lead solder or perhaps a tin antimony solder. And you'll see those joints are neat. You don't see a lot of solder slopped around the pipe. You don't see dripping of solder off the bottom of the fitting. The person that put that together knew how to solder properly and also how to wipe that joint down. It is important after a joint is soldered like this that you wipe it down. You want to get that residual flux off the pipe. We've seen, unfortunately, we've seen too many projects where somebody will solder the joint. They might partially wipe the joint down, but they're leaving residue of flux on those joints. And over time, that acid in that flux will cause a greenish blue surface oxidation, a patina, and it really looks bad on the outside of the pipe. So I'm kind of a stickler. Make sure you wipe the joint down. In fact, we even like to see the joints wiped down with a rag with some detergent just to clean that solder flux completely off the joint. Now, again, I included this table over here so you can see some of the temperature pressure ratings for soft solder joints with two different types of solder. 50-50 is still certainly my favorite solder to work with. It has a lower melting point. It's just an easier solder to work with compared to 95-5. 95-5 has a higher melting point and a narrower molten range, which means you've got to develop a little more skill. You've got to work a little faster and have a hotter torch to work with that effectively. You'll see the pressure ratings go, they change with the different tube sizes and the temperatures there. Basically, as you go up to larger tube sizes, the pressure rating on the joint goes down. But again, the pressure relief valve in most smaller residential light commercial hydronic systems, it's common to see a 30 PSI pressure limit. So these pressure ratings are well within the capability of soft solder. Okay. Now, brazing. Brazing differs from soft soldering. The flux is usually in the brazing rod itself. You're using an oxyacetylene torch. You need higher temperatures, well up 800 to 1,000 degree temperatures for a braze joint. The photo that you see here actually has both solder joints and braze joints. The braze joints are actually made down here at the header. And this would be an example of a product that very likely was not built in the field. It was probably ordered as a header like that. And this type of connection down here is called a T-drill connection, where a very specialized tool drills a hole through the pipe and spins as it comes back up out of the pipe, and actually spins, mechanically forms a collar on that copper tube. And you'll see if you look carefully, that collar is not as deep as a standard socket on a soldered copper fitting. So a solder joint there just doesn't have the proper surface area or the proper engagement length to develop the strength. So a braze joint would be used there. The solder joints are up here, up above the zone valves here, but and below the ball valves. So brazing is used in specialized applications like this. It's not common to see an entire system of hydronic or plumbing system brazed. I suppose it would be possible. Brazing is done more in the refrigeration industry and to build up these specialized components like a header. Steel pipe, groove welding. The fitting and the pipe are mechanically prepared to create a V-shaped groove where the fitting and the pipe come together. And then what the welder is going to do is make sure that the fitting and the pipe are properly aligned. They're going to do a tack weld just to hold the alignment. And once they verify the alignment, they're going to work their way around the outside of the pipe. And there's certainly different welding procedures here. Today, a MIG type welding or TIG welding would be used. And you can see the welded joints here in a couple places on this reducer coupling. And depending on the service of that joint and depending on the size of that joint, some of these joints are actually done with multiple pass welds. And as the weld progresses around the pipe, there's going to be a slag formation that has to be ground away on each pass. So we're right down to the base metal and the welding metal. And then another pass is made, and then the slag is removed through grinding and so forth. And then in very critical applications, something like perhaps a power plant application or high pressure steam application, those joints might even be x-rayed to make sure there's no voids that could potentially cause a mechanical problem, even potentially an explosive failure of the joint under very high temperatures. Okay, now another switching from metallurgical joining over to mechanical joining, and certainly the most common mechanical joining is going to be threading. And that in North America, that is done with the national pipe thread as the standard. This is a tapered thread, and that differentiates it from a thread on a bolt. A thread on a bolt would be a parallel thread. So you could, in theory, you can, in practice, you can take a nut and thread it all the way down through the threaded length of the bolt. Well, with a tapered thread, the threads eventually create an interference fit. So as you continue to tighten the joint, you get more and more resistance, and obviously you're going to need a set of wrenches one on each side of the joint to tighten it up. And very common practice here is to use either a thread sealant, what's commonly called pipe dope, and there's, again, different products out for different temperatures and different fluids, or a Teflon tape. And the idea there is that those materials are going to fill the microscopic fractures and cracks in between the male thread and the female pipe thread as that interference fit develops. So they fill that in, and done properly, that joint is going to seal well. In theory, you can take a joint like this apart any number of times. Each time it would be reassembled. There would be the pipe, and any residual pipe dope, I would say, or Teflon tape should be cleaned off. Fresh dope, fresh tape, tighten the joint back up again. So you can see over there on the right some fittings that have been joined together. In years past, it would be possible. I can recall seeing hydronic systems entirely assembled with threaded joint fittings. Nothing wrong with that, except today that's pretty expensive from a labor standpoint compared to some of the joint systems that go together a lot faster. So today you may see threaded connections like this, certainly on components like a boiler or threading into a tank, an expansion tank threaded into some type of a connection. But it's not going to be a joint system that's commonly used throughout the entire hydronic system, just due to labor costs. Now, another mechanical joining method that uses threads is what's called British Standard Pipe, or BSP threads. And the important distinction here is that these threads are parallel, not tapered threads. And a parallel thread is like a bolt thread. A parallel thread would allow you to take the nut and just simply keep turning it. As long as there are threads that can be engaged, there's no interference between the nut and the thread, unlike a NPT tapered thread. So the thread is simply a way to create mechanical force to bring these components together. The seal, in this case, is actually made at this sealing disc right here. And again, it could be a material, a gasket type material. This particular material will expand once water hits it, so that further enhances the seal. Some fittings like this that would use a parallel thread for the mechanical force would also have an O-ring or some type of elastomeric gasket. But the important thing to recognize is the seal is not at the thread, so there's absolutely no purpose in putting Teflon tape or pipe dope on those threads as you draw that together. Another mechanical joining system, what's called Euroconical connections, and these are commonly used on manifold systems. Again, up here at the top, you see a PEX, aluminum PEX tube, kind of a disassembled joint. And you'll see over there on the far right that there is an insert fitting that has two small O-rings on the neck of that fitting. Well, to prepare that tube, there's a device that goes in and actually cuts a chamfer on the end of the tube. So what that does is it creates a taper in the PEX and the aluminum layer in the tube, and that simply allows those O-rings to go in, that insert fitting to go in without creating forces that could damage the O-rings. The blue polymer ring that you see there, that's called a ferrule, and the ferrule is in there to be compressed. It compresses the outside surface of the tube as the nut on the far left over here is tightened up. So the seal is actually made where those O-rings join the inside diameter of the pipe. The balance of that fitting is essentially a mechanical system to pull the components together with sufficient force and sufficient compression of the tube wall that you get a pressure tight seal at the O-ring. Again, I've seen joints like this hand tightened that don't leak. I'm not suggesting that's what you want to do, but it shows how good that sealing system is, where somebody could put this together and simply hand tighten that nut on, and the joint would not leak. You're going to snug that up with a wrench, but you don't have to use incredible force on this. Basically, the idea, if you understand the mechanics of the joint and how the seal is made, you'll understand you don't need to really torque down heavily on that nut to create a good seal. This happens to be PEX, aluminum PEX. Very similar fittings are used on PEX tubing, or can be used on PEX tubing. The threads that are involved here, again, are parallel threads. They're there just to pull the components together. And we get over to flange joints. Again, these have been around for decades. Flanges are available in several configurations. You can get flanges that thread onto pipe. You can get flanges in this illustration here on the left. You'll see a flange that is designed to slide over the outside diameter of a steel pipe. It's then going to be welded to the outside of that pipe, so that welding is going to burn into the surface of the pipe as well as fill up that tapered groove in the flange itself. And over on the right side of this joint, I'm just showing a symmetrical joint. So this would be essentially a coupling using flanges. Now, flanges are pulled together with bolts. So again, the bolts are providing the mechanical force to draw the pieces together, but the seal is actually made at some type of a gasket that's inserted between the faces of these flanges. And over here on the right, it's kind of a zoomed in view here. If you look carefully, you'll see that there are some fine serrations on that portion of the flange, and those are designed to essentially bite into that gasket to provide a seal. Again, a flange joint could be opened up at any point. It's obviously more work than opening up a union, because all the bolts would have to be removed. The next slide shows you some of the service capabilities, and let me just mute something here for a second. You'll see different classes of flanges, and basically these refer to the thickness of the flange and relate that to the maximum service pressure. You'll see the service pressure actually decreases as the temperature of the fluid increases. Typically, a class 150 flange is very sufficient for hydronic systems. If you're dealing with very high pressure steam, you may be up into a class 600 flange. Over on the left, there's an example. This happens to be a balancing valve. You can actually see down here the flow meter that would indicate the flow rate going through there, but this is a flange type connection. And flanges are built to standards, ANSI standards. Depending on the pipe size, there could be 4, 8, or 12 bolts. Basically, as the size of the pipe goes up, the bolt count goes up. And these have all been calculated decades ago to result in a certain rating, a pressure rating as a function of temperature for a given thickness of flange. Okay, so another mechanical joining method, a bit more contemporary here. This is a groove lock type of system, a grooved joint system, I guess we'd say it generically. It's kind of an interesting concept. Each end of the pipe is prepared with a groove. You can actually see the groove right here in the pipe. With some pipe sizes, it is possible to use a manually powered tool to create that groove. Most production piping with this type of joinery is going to use a power tool to create that groove on both pipes. And then the fitting comes apart. You take the bolts out of the fitting, and the fitting is typically a cast iron body held together with those two bolts. And if you look carefully at the cross section here, you'll see that there's a specially shaped gasket that spans from one side of the pipe to the other. And it's an interesting concept. It's called a pressure responsive seal. What happens here is the pipes don't actually touch each other. And that's good from a number of standpoints. It allows a little bit of expansion and contraction movement. It also allows a joint like this to flex slightly, such as a minor tremor in the earth. I'm not going to say it's going to survive any kind of an earthquake, but it does allow some flexibility at the joint, which is not what you're going to get with a flange joint or with a welded joint. Now, the pressure responsive seal, what happens is the fluid goes back up into this joint right here, and it actually causes the gasket to press tighter against the outside surface of the pipe. So as the pressure inside the pipe increases, so does the integrity of the seal between the outside surface of the pipe and this gasket. This was originally developed around steel pipe, but today there are systems like this that can be used for PVC pipe as well as copper pipe. Another mechanical joining method that has a long history is a flare joint. You don't see a lot of this in hydronic or plumbing systems. Flare joints are commonly used in refrigeration systems. A flare joint is made by using a special tool. Over here on the left, you'll see a flare bar. You'll see there's different pipe sizes. And the idea is that you'd slide the pipe into this bar, you tighten these wing nuts off so it clamps it and it holds it. And then this flaring yoke slides over the bar, and there is a mandrel. And think of this sort of like a nose cone. And as you turn the handle on this flaring yoke, you force this mandrel into the end of the copper tube, and with sufficient force that it actually causes I like to call it a trumpet bell, where it flares the end of the tube out in a very specific angle, a 45-degree angle. And when the flaring of the copper tube is done correctly, the angle of the flare will match up with the angle of a machined brass surface. And so basically, this is a metal to metal seal. You're going to bring these two pieces together. You're going to turn the flare nut tight, and that's going to, again, mechanically draw the flared end of the copper tube against the machined end of the brass. So again, the threads on this fitting are simply to create the force necessary. They do not need to have pipe dope or Teflon tape on them, and the seal is not created at the threads. Now, there's another variation on a flare joint. It's called an inverted flare. And down here at the left, here's an example. It's a Caleffi zone valve with a tailpiece that has an inverted flare fitting. One of the potential limitations on a standard flare joint is that if the nut is over tightened, you can actually cause enough radial stress to crack the nut. That won't happen with this type of a joint. It's a different stress distribution. So these types of joints are able to handle higher stress. I know these are used in applications where vibration can be present. So for example, in brake lines, you'll find inverted flare joints. This particular joint right here, you can see you could back that brass nut out and disassemble that joint without damaging the joint. So it's similar to a union in that respect. If that zone valve body for some reason did have to be replaced, it would be possible to back out this, again, this flaring nut right here and put the new body in and then retighten the joint. The threads, again, only provide the force necessary to pull the tube up against the machined brass surface, metal to metal seal. Brings us up to probably one of the most recently developed mechanical joining methods, what's generically called a push-on fitting. And this is kind of an incredible fitting. It allows you to take a tube and literally just push it into the fitting without any type of adhesive or thread sealing or turning. And as you push the tube into the fitting, if you look carefully in that fitting, you'll see there's some very sharp, small stainless steel teeth. And these point in towards the inner portion of the fitting. So as the tube slides past them, they give way, they bend out of the way, and they allow the tube to slide in. And basically the seal is made at an internal O-ring. And then if you try to pull the tube back out, that's where these teeth basically bite into the surface of the tube and resist that outward pull. And the more pressure that's exerted on the joint, the greater the grip of the teeth against the outside surface of the tube. Down below, you'll see that the manufacturers of these fittings have developed quite a line of products. You'll see some manifolds that are there, specialized fittings, valves, and so forth. I would say the primary market for these types of fittings today is a do-it-yourself market. They are probably as easy as any pipe fitting could be to put it together without a lot of skill and get a joint that's going to last. They are more expensive because of the details of their construction. They have potential to be used in hydronic applications. That being said, I don't see a lot of systems going in with these. Certainly extensively used in hydronic systems. We just don't see that at this point. The other thing I should mention, you can pull the tube out. There's a special ring that slides over the tube, and you basically press in on the end of the fitting. You'll see this little plastic collar that extends outside the fitting. If you press in on that, that will basically lift the stainless steel teeth temporarily. It'll lift them off the outer surface of the tube, and then you can pull the tube back out. So they are a very, I guess I'd say, an ingenious invention, and I'm sure very well patented. They're widely available today in the big box stores and so forth. Again, primary market would be do-it-yourselfers that maybe they just have to put a T into a line to add a lavatory. They're adding a bathroom, that type of thing. These are excellent for those kind of applications. Now, another contemporary method, and this is really starting to get some traction, this is a press joint. And these go back probably origins somewhere in the range of 15 to 20 years. European origin, but widely used in North America now. It counts on a special fitting. You'll see an example of fitting over here. And that fitting has an internal O-ring. The idea is that you would cut the tube. It would be cut square, ream the tube out, take out any sharp edges on the outside or the inside of that cut joint. You slide the tube into the fitting, and then you'll see over on the left here an example of a press tool. And these are typically, these are electrically operated tools that can put very high mechanical force onto the portion of that fitting that contains the O-ring. And you can see that once the joint is pressed, it's not really round, it's hexagonal shape. You can actually see it pretty good right here. One of the really nice features of press fittings, besides the fact that you don't need solder and flux and a torch, is that you can actually make a joint like this with water flowing through it. Now, I'm not suggesting you're doing this with a huge high pressure water stream coming out the end of it, but oftentimes in plumbing work or even in hydronic work, if you're adding a connection to a pipe, you may have a trickle of water. It's sometimes difficult to get all the water out of a system. And if you've ever tried to do a solder joint with any water in that vicinity of that joint, you'll know that that doesn't work well. What happens is you cause the water to flash over to steam. The steam obviously is an increase in pressure, and it will simply blow the molten solder right out of the joint. And you can continue to feed the solder as long as there's water in that pipe and there's steam. You're not going to get a seal. So with a press joint like this, let's say you were going to add a zone valve to a system, you would probably still isolate that portion of the system as much as you could, and you would probably try to drain as much water as practical. But if there was a small trickle of water, and you can actually see that in this photo right here, this joint is being made when there's a small amount of water trickling through that pipe. The O-ring will seal against the outside of that pipe, even with that water. So that's a really nice advantage. And we're seeing a lot of use of press fittings in photographs of hydronic and plumbing systems installations. We see a lot more frequent use of press. And that kind of brings us up to our next poll question here. And I'm going to let Kevin run that question by you.
Thanks, John. Okay, the question is, what percentage of your copper tube installations use press fittings and components versus solder fitting and components? So select one of these: 100% of your installations, 75, 50, 25, or 0. So basically, how much are you doing press? So we'll give that a few minutes. I know we're seeing a lot of it here at Caleffi, like John alluded to. Some of our products, the highest runners now have press connections on them. Looks like 50%, John, is the winner at a third of the group. Actually, it ties with 25%. So 25 to 50% of the installations are using press, followed by 21% for 0. And then 100% came in at 4%. So the 4% of the respondents are using it all the time. And 75%, 17% of the installations are using it 75%. So yeah, it's a very popular method for sure.
Yeah, and you know, the availability of the fittings from different manufacturers and the size range of the fittings, as well as the temperature pressure ratings have increased quite a bit over the last couple of decades. There is an investment in tooling. A press fitting is probably not something an average homeowner or maybe a very small self-employed plumbing contractor is going to use because of the investment in tooling. But those that I've talked to, once they've made the investment in the tooling, the allure of a press joint is faster. And again, looking at different manufacturers, they can claim overall cost savings. Even though the fittings are significantly more expensive, the installation time goes down substantially. So the total of the installation time and the material cost, a common claim is that perhaps an overall savings in a range of 30% when you consider labor and materials. So yes, there's a strong increase in the use of press fittings, and there's a lot of components, air separators, for example, as well as other components, pressure reducing valves that are, well, were traditionally supplied as either FPT threads or as solder type connections. A lot of that is being offered now as press, as an option. Okay. So we've got a few more here, mechanical joining methods. This is one that's been around a long time, a compression fitting. This is typically used where you're adding a shutoff valve under a lavatory, and of course traditional methods were copper tubing. And the idea here is that you cut the tube square, and I can vouch for the fact you do have to cut that tube square. If that tube is not cut square, you're not going to get a good joint here. You slide a brass ferrule over the tube, and then you have a nut that tightens up against a parallel thread on the valve. And basically, again, the nut and the thread on the valve provide the clamping force. The seal is actually done between the brass ferrule and the outside surface of the tube. I guess I would label this kind of a traditional method of putting together isolation valves under lavatories. This particular style isn't used a lot in hydronics, but it's kind of a product or a joining method that's used more in the plumbing side. That's kind of given way to compression joints where today many times the connections under a sink are done with these hose assemblies, and these hose assemblies have an elastomeric gasket built in. So the idea is pretty simple. You just connect these together. You take a wrench and you tighten that up, and the seal is actually done at the elastomeric gasket. Much faster, and quite honestly, this is a lower skill set to put something like this together. If you can use a pair of wrenches, you can basically put together, and these have good reliability. So a lot of the under lavatory type connections, perhaps the water connection to a water closet, common application for this type of a compression joint. The photo over on the right here, you can see an example. Here's a thermostatic mixing valve that would be under a lavatory, and it's been configured so that these hose assemblies can tighten up to it. Again, no soldering, no mess. So in what time we've got left here, and we do want to allow some time for questions at the end, I want to run through very quickly just some examples of polymer piping materials. And we'll start off with, oops, let me just go back. Start off with a very common one, PVC, polyvinyl chloride, extensively used for drainage, waste, and ventilation piping. If you've been in any residential, light commercial construction, you've likely seen this Schedule 40 PVC pipe. It is being used, it's rated up to around, if memory serves me, I believe it's in the range of 140, possibly 149 degrees Fahrenheit. It's certainly not a pipe that you would use for 200-degree water distribution in a hydronic system or steam, anything like that. Again, its most common use is going to be in drainage, waste, and ventilation piping. Now, another variant of basic PVC is chlorinated. There's more chlorine in this pipe. It brings it to a higher temperature pressure rating compared to PVC. And the common application here in these smaller tube sizes is residential water distribution, hot water, cold water distribution. These tubes and fittings are put together with a solvent weld process. with chemicals that actually soften the plastic on the pipe as well as the socket on the fitting. And then those plastic materials, as the solvents evaporate, they bond together. It's a permanent joint. There's no way to take that apart short of taking a saw and cutting it apart. So you do have to kind of plan out what you're doing here before you glue these joints together. In larger pipe sizes, CPVC in some applications is being used for venting boilers. I know that's been done up in Canada, 636 standard for a while. I think there's probably some domestic use of CPVC pipe on boiler venting. PVC pipe, there is still some use of that for boiler venting. I would urge extreme caution if you're considering that. Look into it. You'll find that PVC pipe is not, it's not certified by the manufacturer for that type of application. It is a plumbing product, not a venting product. So now, next one, high density polyethylene. This is being used for a lot of things today. Here we're looking at some 1,000-foot long coils of 1-inch polyethylene, high density polyethylene. It's being rolled out in a ditch. This is part of a ground coupled heat pump system. This kind of pipe is also used for bringing water in from wells. It's being used for water service entrances from municipal mains. It's being used for gas services, a specific wall thickness, SDR 9, I believe it is, standard diameter ratio 9. And by the way, I should mention the Hydronic 26 that is paralleling today's Coffee with Caleffi. That goes into more detail than we have time for with these slides. If you're wondering about different wall thicknesses, and for example, SDR 9, standard diameter ratio, that's a ratio of the outside diameter to the wall thickness of the pipe. These concepts, these definitions are explained in more detail in Hydronics number 26. So again, a pipe that can be used for a lot of different things. Another thing about this pipe, this is a thermoplastic, which means it can be melted and bonded together through what is called butt fusion or socket fusion, where you're literally melting the ends of the pipe, pushing them together in that molten state and allowing that to cool down. Extremely strong joint. Really, the use of fusion joining and high density polyethylene pipe, I would have to say, is the reason we have ground coupled or earth coupled heat pump systems today. Metal pipe and PVC pipe were tried in some very early generation earth coupled. They just couldn't take the stress underground. And remember, the soil moves a little with changes in moisture, changes in temperature, and that can put very high stress on a rigid pipe. So high density polyethylene is really the product that's enabled the earth coupled heat pump industry to develop. Now we move over to a cross-linked polyethylene, and cross-linking is there's several different ways to cross-link it. Essentially, you could describe it as a three-dimensional molecular bonding. Standard polyethylene molecules don't necessarily bond to each other to the extent that it would allow the pipe to go to high temperatures and high pressures. A standard polyethylene molecular structure, there's some movement possible between those molecules. But through cross-linking, you're essentially creating bonds between adjacent molecules that create a structure, a crystalline structure in the material that allows it to go to much higher temperatures and higher pressures. And again, just as I've credited high density polyethylene as kind of the reason we have earth coupled heat pump systems today, I'll credit PEX tubing as probably one of the products that saved the hydronics industry back in the early 1980s. If you look at the hydronics industry in the 1970s, it really wasn't anywhere near what it is today. And the idea of radiant panel heating with copper tubing, there were systems that were put in, and I'm sure there probably are a few that are still functioning, but there were problems associated with copper tubing and radiant panel heating, and that market was all but gone when PEX tubing showed up, I think probably 1981, 1982 timeframe, and it really allowed contractors to have confidence that they could bury tubing in concrete and that it was going to operate at temperature and pressures necessary and last for decades. So it really is what brought the turnaround in the hydronics market in North America. Here's a typical layout of half-inch PEX tubing in a basement. They're going to pour a slab over that. You'll see the contractor's done a nice job. He's put some flow direction arrows to make sure when those tubes are connected to the manifold, they're in the right position. And that tubing has been tied down to the welded wire fabric, and that's sitting on top of extruded polystyrene insulation. So cross-linked polyethylene PEX tubing, it's a thermoset plastic. Once it's cross-linked, you do not melt it. You can't fuse cross-linked polyethylene tubing together the way you can high-density polyethylene tubing. You've changed the material from a thermoplastic to a thermoset plastic, and that's an irreversible process, okay? You can get, I should mention, you can get PEX tubing with and without an oxygen barrier. The oxygen barrier is designed to greatly reduce the amount of oxygen molecules that can, over time, can diffuse through the tube wall and get into the system where they would cause corrosion of ferrous metal. I'm a big proponent of barrier tubing in any hydronic application. It's a very small price premium for the insurance that it brings to make sure that you don't have that type of corrosion. Non-barrier PEX, primary use on that is plumbing. Today, it's common to see it in two different colors. You can get it in red for hot water, blue for cold water, simply to keep track of which is which. And there's no need to put an oxygen barrier on a plumbing tube because you have fresh water going through it, and fresh water has dissolved oxygen. So now we'll move on to I guess I'd call it a derivative product of PEX. This is PEX aluminum PEX. And you'll see in the cross section here, we've got a thin layer of aluminum that's actually welded together. It's overlapped and welded here. And this is sandwiched in between two layers of PEX. And those materials, the two layers of PEX and the aluminum, are held together with a very high-tech adhesive as the pipe is actually fabricated. One of the nice things about PEX aluminum PEX is when you bend it to a shape, it pretty much stays in that shape. So when you're bending a U-turn, for example, putting this material down, it doesn't tend to recoil the way a PEX tube, especially a cold PEX tube would. The aluminum layer also provides a really good oxygen diffusion barrier. All PEX aluminum PEX tubing is a barrier tubing. And it has a relatively low coefficient of expansion compared to PEX. And there's quite a difference there. I'm a big proponent of using PEX aluminum PEX whenever there's aluminum heat transfer plates going into the system. And you'll see a photo over here on the right where half-inch PEX aluminum PEX is being pushed down into the grooves of these aluminum plates. The reason I like this combination is that the expansion of the tube and the plate are almost identical. So as that system changes temperature, you're not going to get a lot of expansion movement of the tube relative to the plate. And that kind of a movement, if it's present, can tend to cause ticking sounds, expansion sounds. So personal preference, it's not a code. It's simply a personal preference. With aluminum plates, we like to use PEX aluminum PEX tubing. It does have a little higher temperature pressure ratings. This could be used for baseboard systems. It can be used for, if memory serves me, up to about 210, 215 degree water if necessary. It can also be used with compressed air systems. And then finally, we're getting to a newer polymer material. It does have a track record in Europe, probably in excess of 20 years now. It's called polyethylene raised temperature, or you'll hear it referred to as PERT tubing. And this is not cross-linked. PERT tubing does, the polyethylene does undergo some type of a chemical process that modifies the crystalline structure, but it is not cross-linking. And that means that a PERT tube can actually be joined with socket fusion. You could get a coupling and a special heating tool that would heat the inside of the coupling, the outside of the tube, and you can actually press these together and they will bond just like a polyethylene tube will bond. If you look in Hydronics 26, you'll see that the pressure temperature ratings of this tubing are high enough that it can be used in just about any kind of residential or light commercial hydronic system. One of the marketing points with this tubing is that it's more flexible than PEX tubing. And that's going to bring us up to another poll question. And this is our last poll question. And Kevin, I'm going to let you take it over there.
Yeah, I think we may have one more after this, but this one is, what percentage of your hydronic radiant panel or snowmelt installations use PERT tubing versus PEX? So who's using PERT out there? Please select either 100%, 75, 50, 25, or 0 in terms of what percentage of your installations are using PERT. Let's see what we come up with.
Yeah, and as those numbers are coming in, PERT is not as widely available. There simply aren't as many product offerings, but I would look for that to change as we go forward.
Well, 83% of the respondents said 0. So not too many. Okay, 8% said 25% of their installations are using PERT, and then very little for the rest. So pretty much overall, not a lot of installations are using it.
Okay, you know, I should just throw out an idea. One of the things I like about the idea of PERT tubing, the ability to join it with fusion. Imagine you're doing radiant panel systems, and oftentimes you end up with remnants that might be 20, 30, 40 feet long, and they really aren't long enough to be used for other radiant circuits, and you're hesitant about using some type of mechanical joining system and burying that tube, especially in a concrete slab. Well, with a fusion joining, you've got an extremely reliable joint, and imagine you could take some of those remnant pieces using a fusion tool, put them together, and actually create a piece long enough to be used for another radiant circuit, or perhaps a snow melting circuit, and have very, very good confidence that that joint is never going to come apart. There's no threads. It's literally fused into a single piece of plastic. So I remember a few years ago seeing a demonstration of that in Europe, and I was quite impressed by the fact that you could use fusion joining on this tube. Whereas that is not something you can use with a standard PEX tubing. And you're right, Kevin, we do have another poll question. Okay, so just a couple more here. A standard way to connect a metal fitting and a PEX tube would be with a crimp ring. It's a very simple idea. You're going to cut the tube square, you're going to slide it over that ribbed area on the fitting, and then use a tool. And these tools are manually operated tools. I'm sure you probably can buy a power tool that can do that today. But this provides sufficient clamping force to cause that copper ring to crimp in on the tubing, and the seal is formed between the PEX and the insert portion of that fitting. Again, these are commodities. You can buy these in the big box stores. It's a pretty common method. It does require that you have that tool, but that tool is not thousands of dollars. It might be $100 or $150, not $2,000, $3,000. The tool would have different jaw inserts for the different sizes. And when a joint like that is made, it's common to have what's called a go, no-go gauge. After you've crimped it, you basically slide this gauge over the fitting, and if the gauge doesn't slide over the ring properly, you don't have a proper press on that ring. So again, this is a common joining system for PEX. Another one that's out there is called a cinch joint, or I believe it's pronounced Oetiker clamp joint. I don't have much experience with this, but the idea is pretty simple. You're going to slide a stainless steel ring that's specially formed. You can slide that over the tube. The tube slides over the fitting, and then the tool that you see over on the right is being used to actually not crimp around the entire joint, but to actually draw the radius, decrease the radius of that ring by simply drawing excess material out and creating what's called a cinch. So again, It's a manually operated tool. Because it is a stainless steel ring, it might be good in applications where there's going to be condensation on the joint and so forth. Just another mechanical method. And the method that I think is gaining popularity just based on photographs that I'm seeing is what's called cold expansion joints. And this relies on PEX tubing or PERT, but I'll get more specific. It relies on the shape memory of PEX. When you take PEX tubing and you expand it, those molecules try to go back to their original state. So using very high force with a tool, you'll see here there's a tool that basically inserts into the end of the tube. There's serrations on that, the portion of the tool that goes inside the tube, so it doesn't slide out. It does have a taper to it, but you also notice there's another ring of PEX tubing around the outside of the tube. So it's very important that that ring is there. That adds thickness and mechanical strength. So you're going to put the ring on the end of the tube, you're going to expand the end of the tube, you pull the expansion tool out, and you immediately push the tube and the ring over the, in this case, it's a brass fitting. And I should mention that the details on that brass tailpiece are different for cold expansion joints compared to the crimp joint. So you want to make sure you get the right type of joint. The standard is the ASTM F1960. Now, what happens within a few seconds is the ring and the tube itself will start to contract back to their original shape. And just given maybe perhaps a minute or two, there will be sufficient compression at that interface between the brass and the PEX that you have a leak-free joint. It's not a reversible joint. Basically, the only way you could take that apart would be to carefully cut the ring and the tube and pull it off. But it is a fast joint. Again, a specialized tool is required, but you can get manual tools that will do this perhaps in the range of $200 or $300, or if you're doing a lot of this, you can get power-operated tools. This is also usable with PERT, but I have to stress the ring that goes around the PERT tubing has to be PEX. PERT does not have the shape memory. It's not a cross-linked material. So it's counting on the PEX outer ring and the shape memory of that outer ring to provide the compression for that joint. And this does bring us up to our final poll question. So Kevin.
Okay, here we go. What percentage of your PEX or PERT tubing installations use cold expansion fittings versus crimp ring fittings? So what percentage is using cold expansion versus crimp ring? 100, 75, 50, 25%, or 0%?
Yeah, we're seeing more interest in things like joining PEX tubing to zone valves using this. So what do we have, Kevin, here for a result?
Okay, 16% of the respondents said 100% of the time. So they're using cold expansion. 14% said 75% of their projects. 16% said 50, and the same for 25%. And 37% of the respondents said that they don't use cold expansion. It's 0%.
Okay, so roughly a third of people are using something else, but 2/3 at least at times are using this. So again, I think this is a method, just because of its simplicity, is probably going to gain some market share as we go forward. Okay, so we'll go back and we'll wrap this up. Oop, I skipped, here we go. I wanted to show this. This is a compression, a mechanical compression, or a press type of fitting. It's not the same as a copper press fitting. This is specifically for PEX, aluminum PEX. This is a fairly complex fitting. It has interior O-rings on the brass interior cylinder, and you would prep the tubing with a mandrel that would cut a slight bevel on the tube. You would press the tubing in, and you'll see there's a little hole in the fitting right here. The idea is that you want to see the end of the tube go all the way down and cover the hole. That indicates that it's been pushed all the way in. And then the tool, and this is usually a power operated tool, although I believe there are some manually operated variants on it, that presses the stainless steel sleeve in actually 3 different places. So you get mechanical compression of the stainless steel sleeve on both sides of both internal O-rings. So you have a double O-ring seal at each connection. So for example, if you wanted to connect a male adapter to take a half-inch PEX aluminum PEX over to a valve, we're showing a coupling here, but there are several different types of fittings.
And with that, John, thank you very much for today's session. That was excellent.
You're welcome.
And everybody out there, thanks for being here. We'll see you next month. Bye-bye.